Hey guys, Mr. Smith here, and in this video lesson, our fourth lesson of Unit 5, we're going to be solving some trigonometric equations. So let's get started. So there's a whole slew of reasons why we want to be able to solve trigonometric equations. Um, um, One application is described here in the introduction for designs of skis and like kind of optimizing performance. Another example that I use when I teach my calculus class is like an eaves trough that goes in the side of your house. So an eaves trough is like attached to your roof, and like generally speaking, when the rain hits your roof, it goes down the shingles, and instead of just like falling over your house, it goes in the eaves trough. It collects and runs out the spout. And the way those are made, they essentially take flat sheets of metal, and then they kind of fold up the corners, something like that, at a certain angle. And it's a really useful question: what angle would you fold at to give the biggest cross-sectional area for your eaves trough? So if it's raining really, really, really hard, as much water can flow through as possible. And finding that angle ultimately involves solving a trig equation. And it actually involves, I think, from examples 1 and 2 today, those types of equations pretty closely. So let's get started. As we solve these next level trig equations, we'll be relying on skills we already have with respect to solving trig equations. Namely, if we have a trig ratio like sine theta equals a half or secant theta equals root 2, we already know how to use the unit circle and the cast rule to find angles. We're just going to be making use of that. So let's dive right in. The first equation we're going to solve today is this one: 2 times sine x squared minus 1 equals 0. So it is a quadratic trig equation in that the trig ratio in it is squared. And so we're going to solve this equation by hand, and then we are going to check using Desmos. So here we go. Now with this particular equation, we can actually just kind of isolate the sine x by being careful. We can move the 1 to the other side, divide both sides by 2. And we have to be careful. There's 2 values for sine x here that can give us 1/2 if we square root both sides. And that's 1 over root 2, but also negative 1 over root 2. So you have to be really careful if you're solving equations like that. Like, for example, x squared equals 1. There's more than one solution to that, right? 1 squared is 1, but also negative 1 squared is 1. So when you're solving quadratic equations like that by just taking a square root, you got to make sure to include both the positive and the negative. So now we're asking ourselves, well, what values for the angle x will give us a sine ratio of 1 over root 2 on the interval from 0 to 2 pi? Well, we got to look at it individually. So let's look at our first case. Let's look at the case of where sine x equals 1 over root 2. Now your calculator can give you an approximate value in radians or degrees. We're going to stick with radians. But this is one of our special values on the unit circle. So I'm going to draw a diagram of the unit circle off to the right here. And I'm just going to pop in my cast rule, CAST. So there are 2 quadrants where the sine of the angle is going to be 1 over root 2. And we know from our unit circle, one of those, I'm actually just going to draw a big unit circle too, and just add some details to this. Not a bad circle. We know the first angle where the sine is 1 over root 2 is the angle pi by 4 radians, corresponding to the point 1 over root 2, 1 over root 2 on your unit circle. And for this lesson, having your unit circle handy would be great. So if you want to pause and print that up or print that off or pull out your binder or bring it up in a separate window. The other angle that's going to have a sine value of 1 over root 2 will be in the sine quadrant. Also makes an angle of pi by 4 with the x-axis. And of course, that angle is 3 pi by 4. And this corresponds to the point negative 1 over root 2, 1 over root 2. So we're making use of our unit circle and the cast rule there. Get back to my blue pen here. All right, so we can, I'm just going to write a little blurb here from the unit circle and the cast rule. Here, x can be pi by 4 or 3 pi by 4. Now what we're going to do is we're going to repeat that process. We're going to do it for sine x equals negative 1 over root 2. We're going to get 2 more angles, making 4 in total. And as we move forward and do more of these, we might streamline this process of drawing or finding angles using the unit circle and the cast rule. Let's continue. So our second case is if x is negative 1 over root 2, sine x is sine x. So in the same way, I'll draw a rough sketch of my unit circle, cast rule. And of course, now we're looking for when sine is negative. We're in the bottom 2 quadrants, and we're looking for angles. They're going to be related to pi by 4. They're going to make an angle of pi by 4 with the x-axis. And of course, we know these 2 angles are, I'll just use a different color for labeling. So that angle there, 5 pi by 4, corresponding to the point negative 1 over root 2, negative 1 over root 2. And then maybe a purplish color will be good for the next one. And then this is 7 pi by 4, corresponding to the point 1 over root 2, negative 1 over root 2. And again, from our unit circle and the cast rule, we get 2 more angles. That would be 5 pi by 4 or 7 pi by 4. And I won't write like in the previous slide from the unit circle and the cast rule. I've done my diagram. I've shown that work, and it's just kind of expected that we can kind of read that off. But when you guys are solving equations for me, if you are using your unit circle, I'd like you to do a similar diagram like I've got here, just to make sure you understand what's going on. And this, not that you're just reading the solutions from some program or something. Just maybe make a little concluding statement. All the solutions on 0 to 2 pi are, we had 4 of them: pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. Let's head to Desmos and just confirm that. Desmos. So what we can do in Desmos is we can graph the function y equals 2 sine x squared minus 1. That's what we're working with, right? Yep. And then asking ourselves, when is this equal to 0, right? Our equation was, when is this equal to 0? And on from 0 to 2 pi, and I might just change my settings here. I might go from let's go from -1 to 2 pi to 7. And we can see pi by 4, close that out there, pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4 on the interval from 0 to 2 pi. So that's great. So let's continue. Okay, so a question we're going to do right now that's similar in a way, but different in another way. Here we have a quadratic trig equation because we have a cosine squared in it. We also have a cosine in it. And maybe it's not immediately clear on how we're going to isolate the cosine x, but we can do that by factoring. So if you're wondering why your teachers just made you factor over and over and over and over again in your earlier courses, so we get to this point and we just have that. We have that in our math toolbox. So we can almost treat this as an equation, and you can choose to copy this down if you want to. But almost like imagine that cosine x was just like some other variable u. And of course, that can just be factored to u minus 2 times u plus 1. And we're just going to do the same thing, except instead of u, we have cosine theta. So we're going to factor. And that gives us the following. Cosine x minus 2 times cosine x plus 1 equals 0. And now we can solve this equation by setting each factor to 0. So we have two possibilities. First possibility is that cosine x minus 2 is equal to 0, which gives us cosine x equals 2. And maybe have a quick think about that. Is it possible to have any solutions for x that give a cosine of 2? And the answer is no, right? Our basic knowledge of the cosine function, highest and lowest it gets, 1 and -1. It is impossible to get a cosine value of 2. We get no solutions from this branch. So let's look at the other one. What values of x make cosine x plus 1 equal to 0? Well, that's when cosine x is equal to -1. And you can use your calculator. It would spit out the angle in degrees. If it's in radians, it'll spit it out. Probably won't spit it out as a multiple of pi. But we know the solution. The only angle between 0 and 2 pi that has a cosine of -1 is pi radians, or 180 degrees, right? Corresponding to the only point on the unit circle that has an x value of -1. This guy, right? Cosine of pi is -1. And this is the only solution on 0 to 2 pi. And we've shown it. We've looked at all the cases. Cosine can't be 2. And the only value between 0 and 2 pi that gives a cosine of -1 is pi itself. So the only solution on our interval from 0 to 2 pi is x equals pi. All right. So kind of similar in a way, we got two cases, but we got those cases by factoring our quadratic expression. Sip of coffee here. Shooting relatively early in the morning, just squeezing this in. Okay, let's check our answer in Desmos, actually. So let's head there. All right, and we're going to type in a new function. And to square cosine, I just put in brackets. And then minus cosine x How cool is that function too when you square cosine? Minus cosine x minus 2. When does that equal 0? Well, first of all, that is a cool looking function. But secondly, we can see that, yeah, the only time this is equal to 0 is when we get x equals pi. So pretty neat. Let's get back to the lesson. And yeah, let's continue. All right. In this question, we're going to apply some of our skills, but we're going to mix in some reciprocal ratios here. So looking at the equation, 2 times cosecant x squared plus cosecant x minus 1. Our immediate reaction should be, okay, it's quadratic. It looks like I should factor this one. And for this one, we're going to, because the coefficient in front of the quadratic term is not 1, we can't use simple trinomial factoring. So I'm just going to actually replace cosecant x with u and just write 2u squared plus u minus 1 equals 0. Just because it'll be a bit less clunky as I'm factoring. So let's factor. So we're looking for, well, I'll use decomposition here, looking for numbers that multiply to minus 2 and add to 1. Those numbers are 2 and negative 1. Group factor, 2u times u plus 1 minus 1 times u plus 1 equals 0. So we get u plus 1 times 2u minus 1 equals 0, giving us two possibilities. Either u plus 1 equals 0 or u equals negative 1, which means cosecant x equals negative 1. And let's just finish off this branch while we're at it. If cosecant x is negative 1, then the sine of x is going to be the reciprocal of that, 1 over negative 1, which is just equal to negative 1. And I'll just, don't think I gave myself a second slide. I didn't. So I'll just do this work down the bottom here and then make room up at the top. So when is sine x negative 1? When is the y value on the unit circle negative 1? Down here. So we get one solution from this branch, 270 degrees, or 3 pi by 2. For our second branch, let's have a look. I'll go off to where I have some space. So 2u minus 1 equals 0. Solving that gives us u equals 1/2, which means cosecant x is equal to 1/2. And, before we immediately pull out the unit circle and look for some values, remember we got to write that in terms of sine to use our unit circle. And this gives us, if we take the reciprocal of 1 over 2, we actually get 2. So just like our last problem, we get a branch where there's no solutions. No value of x can make the sine 2. And so we actually just get our one value. The only solution on 0 to 2 pi is x equals 3 pi over 2. So kind of a common theme with all of our examples, guys, either by isolating in our first example, isolating sine x and gave us two possibilities. We had to look at each possibility and get answers from the unit circle and the cast rule. Similarly, with the next two examples, we got two branches or two cases, but we got those by factoring and setting each factor to 0. Sometimes a factor will lead to no solutions. But sometimes, like in this case, in our example 3, we got one branch gave us no solutions. Sometimes each factor will give us meaningful solutions. Much like our third guy. We should check this one on Desmos as well. Always a good idea. And so what was our equation here? It was 2 times cosecant x squared. This is going to be a cool looking function, I can tell. plus cosecant x minus 1. Yep. You can see the only spot on 0 to 2 pi where this is equal to 0, 3 pi over 2. Looks like we nailed it. Great. Let's continue. I think we just got one more problem to do, a little application problem. So a classic application of trig equations is from physics, and specifically projectile motion. Um, uh, you can show that the horizontal range of an object, when you launch it from one height and it lands at another height, involves the sine of 2 times the launch angle. So here the range, which is how far away our arrow is going to fly, is given by 100 times the sine of 2 times the angle, the launch angle. And our target is 80 meters away here. So first of all, before setting R to 80 and finding how we should launch our angle, it's worth thinking about what are the actual possible values for our angle, right? So I'm going to draw a very crude stickman diagram here. There's my bow, and here's my arrow. There we go. But if you think about what are the possibilities, right? Well, we could fire the arrow horizontally, like we're not going to throw it. We're not going to like fling it into the ground. So the minimum launch angle would be theta equals 0. And then what would be the maximum? Like if our target's over here, we're not going to be launching it backwards, right? So the highest it can go is 90 degrees, or pi over 2 radians. So what we're looking for is when we set up and solve an equation, we're only looking for solutions between 0 and 2 pi. Now let's actually, maybe on this slide, because I have my diagram here, I'll set up the equation and I'll solve it on the next page. So for B, that was for A. And I guess I might write the solution to A just off to the side a little bit, make that look a little cleaner. For A, theta must be between 0 and not 2 pi, pi over 2. Okay, we justified that with a little diagram. Okay, and for B, so we're trying to hit a target 80 meters away. So how high should we aim our arrow? We're going to set R to 80. Geez, I can't spell today. I'd blame the early morning, but I can't spell most days. Setting R to 80. And we're going to solve this equation on the interval 0 to pi over 2. We're going to see if we can get any angles. So I'm going to head to whiteboard or my second slide here. And we know this isn't quadratic. We're expecting to get we're going to be, in this case, just using the unit circle and cast rule. Let's keep going. Let's see what this looks like. So our equation, you don't need to rewrite this down because obviously you have it. I don't have it on this slide. 80 equals 100 times sine 2 theta. So let's get solving. So we can divide both sides by 100. And we get sine 2 theta equals 0.8. And at this point, we're going to need to rely on our calculators. We're going to solve this one by hand, like I usually like to do. And then we're also going to check using technology. And when you do an evaluation or assessment for me, I'll make it clear on what my expectations are. But we can solve this one by hand. So we're going to get 2 theta equals, so inverse sine of 0.8. We get 2 theta is equal to whatever that is. We'll make sure we're in radians mode here. Second sine, 0.8. All right, so I got about 0.9273. Which corresponds to theta being equal to, if I divide that by 2, to 2 decimal places, about 0.46 radians. All right. So 0.46 radians. So, whoops. I'm going to draw that on there. So that is lower than pi over 2. So that's somewhere in this quadrant. Yeah, you know what? Actually, I'm going to just call an audible here. So 0. I'm just going to erase this guy. So when we solved for the argument of sine, 2 theta equals 0.923, call it 0. Yeah, we'll just call it 0.923. It's fine. So 0.9273 radians would be something like there. And then we have to remember for the with the cast rule, we get 2 possibilities, right? So we're gonna get a second value off in this quadrant that also makes an angle of 0.9273 radians with the x-axis. And so just keeping a lot of accuracy here, that second angle would be whatever 3.14 minus 0.9273. How many radians would that be? Minus 0.9273. I'll keep a lot of accuracy here, 2.127. Now you might be saying, well, that is more than pi by 2. But remember, this is for, these are the possible values for 2 theta, right? So we get 2 possibilities for 2 theta. 2 theta is 0.923, which corresponds to an angle of 0.46. And I might just go over to this side. Or 2 theta could also be equal to 2.2127, which actually does give you an angle between 0 and pi by 2. Divide that by 2, get about 1.11. So you guys need to be careful when solving trig equations that have like this one, where it's like the argument is like 2 theta. Because here we were looking for solutions on 0 to pi by 2. We actually had to consider values for 2 theta outside that range so that when you divide them by 2, you actually get a solution in the range you want. So keep in mind here, there's actually 2 solutions. Let's head to Desmos and just confirm this. I'll have to change my window as well. So our equation is 100 times the sine of 2x. And we're going to make another function here, y equals 80. See where those two meet. And I'll just change my settings to go, what do I want my y values? Let's go up to 120. And there we go. So you can see between 0 and pi by 2, I actually get 2 solutions. Excuse me. So if you guys were doing this on an assignment, evaluation, pencil and paper, use this as a bit of a check. If you found that first solution, maybe that's the only one you did. You got about 0.46, and maybe you stop there. Checking in Desmos, you can see, oh, there's a second value of about 1.11. And why we got there, we showed you guys in this example here. So yeah, looks like we did okay. Let's just wrap this question up. And then maybe just for for us to help wrap our minds around the problem, maybe let's convert these to degrees just for fun. So, therefore, they should fire at an angle of 0.46 radians. And then maybe in brackets, I'll just do a little conversion of that to degrees. So to convert to degrees, remember we multiply by 180 and divide by pi. So about 26.4 degrees. Or our second solution was 1.11 radians. And if we convert that times 180 divided by pi, 63.6 degrees. So one, we're kind of shooting like this to hit our target, and the other one, we're shooting a lot higher to hit our target. And if you were in an archery competition, maybe you can have a little think on this. If you were in an archery competition, which one would you choose? And I think most of us would choose the one that's at a lower trajectory, because it's going to be a straighter flight, smoother flight. The arrow is going to get there quicker and just allows more accuracy. Even though both, if you could fire perfectly, would hit the target, archers would pick the lower angle. But yeah, so again, guys, be careful solving equations with an argument of something that's not theta. There might be more than one solution, like we did here. Okay. Kind of just rambling at this point. Let's wrap it up. So we've solved some trig equations using a variety of methods. Most of those methods ultimately rely on the unit circle and the cast rule. We did use the unit circle to get our exact solutions for the first three problems. This problem here, the last one, we did not use the unit circle because we had to get approximate values, but we made use of the cast rule, right? Our calculators gave us 0.9273 radians. We had to use the cast rule to know that there's a second value that gives a positive sign, and we had to use the cast rule and subtracting that angle from pi, from 3.14. So after using the cast rule, using using our unit circle, all of our solutions relied on those things. But the strategies we had were considering cases. In the case where we had sine x squared equals a half, we had to consider the positive and negative case. That was from our first example. Or when we have to solve an equation by factoring, we get two cases to consider by setting each factor to 0. And our third example was similar, except we mixed in some reciprocal ratios. So we do have a variety of tools that will help us solve by hand. Of course, we can do it graphically with technology, and I'll make it clear on evaluations what I expect. But using even if I ask you to do it by hand, using technology to check is a great idea. And then, just like our last example, make sure we find all solutions that lie in your domain, because it would have been easy to miss the second guy there. And we kind of introduced a technique where if you have a quadratic trig equation, you can solve it by factoring to get those linear factors where you can use the cast rule in the unit circle. All right. So in our final lesson, we're going to take a deeper look at some real-life applications involving periodic functions, maybe mix in some graphing, maybe mix in some modeling and making equations, maybe solve a few equations. For now, I've got some suggested practice for you guys to work on. All right. Hope you guys enjoyed that lesson. Hope you guys are having a great day, and we'll see you soon.